Yes, welcome our next speaker, Samadrita Mukherjee. She'll be talking around the title, Reinterpreting Bounds from dy pair productions in terms of weak isospin. Over to you.
So, hello everyone. In the last but one talk, so I'll be talking about reinterpreting bounds from pair production via Dralian production, and we will be interpreting our result through isospin quantum numbers. So this work has been done in collaboration with Avik, Dipankar and Shreya, and hopefully you will soon see it in the archive. So what is the outline? So there exists a plethora of BSM models which are designed to actually solve the shortcomings of the standard models, which we happen to hear in all the BSM talks, and most of them predicts existence of spin zero particles with non-zero electric charges, so to say the charge scalars, and they are being produced through Dralian processes. So what is that? It is pp to L plus L minus through photon or Z conventionally. So in place of L plus and L minus we have charge scalar, that is H plus H minus or H plus plus H minus minus depending on the charges. And the LHC collaboration and Atlas and CMS detector, after collecting their data, they routinely employ this method of pair production of this charge scalar to search for those particles, and what they do, so they do these dy searches and interpret their model specific bounds from the experimental data. So we expect that doubly charged scalars are will be producing higher production cross section due to the higher electric charges, because the cross section is directly proportional to it, and it is fairly common in many BSM models. So what is our actual motivation? So as I said, this Atlas CMS collaboration, they routinely employ these dy searches and interpret their data through some model specific limit. So let's say you have 2HTM, you will put a limit, you have type 2 seesaw, you will put another limit, but this work stems from the observation that this production cross section actually depends on these basic properties of the particle. So the number one is mass, the second one is their electric charge, and the third one and the most important one is the isospin numbers. So how these charge scalars are modeled in these BSM theories? So we have different kind of multiplates. So they have the hypercharge and the isospin. So depending on their isospin quantum numbers, we can classify them, and these three properties is the are the sole properties from which we can generate many conclusions about this class of models. So therefore, this generic feature of this production cross section can be exploited to derive constraints on the branching ratios, and this can be used as a effective toolkit of such class of models. And we will be utilizing the most recent experimental data and many phenomenological recast analyses. So let us concentrate on the Lagrangian. So for the scalars, we have three classes of interaction. One is scalar vector boson, the another can be scalar vector boson, and the third one can be fermion plus scalar. So as we are producing two scalars in the final state, we will identify our new physics Lagrangian where two scalars and one vector boson exists. So for the photon, we have this interaction. I wrote it in a general form where Q is the charge of this charge scalar. Then we have the interaction with Z boson, and there we have the W boson interaction where one is SQ plus 1 and one is SQ minus to conserve the charge. And if you want to write it in a general SU2 doublet or SU2 multiplet kind of form, then we have KZQ to be the isospin minus charge of the scalar times the Weinberg angle square, and KW can be calculated after a few lines of calculation, so it's coming out to be this. And very fairly common Feynman diagrams are this, and this is a Dralian production, and through W we have associated production, and the governing interactions are this as I just showed. So we intend to provide a convenient way and an easy toolkit to like we want to catalog these constraints utilizing the current experimental data, and our main point is that dy searches can be concisely classified in terms of charge and T3. So if you are given the charge of your scalar and T3, that is the isospin quantum number of your scalar, then you can easily deconstruct in a model independent way and say what will be the limit on your mass and the branching ratio plane. So it is a general feature for any scalar sector extension model. Here I wanted to just mention about this paper. So it involves all the recast analysis for several kind of scalar sector extension. So starting from the multi-Higgs doublet model, Higgs triplet model, etc., etc. So here in this reference you will find all those. So yeah, so here in this slide I wanted to just flash what is all kinds of model which can be covered in this toolkit. So in scalar sector extension you can have multi-Higgs doublet model, 2HDM is a subset of that. Then there comes Higgs triplet model, Higgs septet model, it has an nasty scalar sector. Then the Mukherjee model, composite Higgs model with some symmetry in that their group sector. Then Z-Babu model, the celebrated leptide symmetric model, all can be classified under this analysis. So here is the table. You can see that when electric charge is +2 for the doubly charged scalars, so we can have T3 eigenvalues as +12, +1, and there can be mixed state for 0 and +1. Doublet, triplet, singlet, the models are listed here, and similarly for a singly charged scalar you can have -1, 0, +half, +1, +3, and there can be the mixed state when before the electric symmetry breaking you have 2 triplet and then 1 real or 1 complex triplet, and via mixing of those 2 triplets you can generate actually a singly charged scalar. So leptide symmetric model and Mukherjee model can be an example for that. So here for an explicit example, consider this process where PP to SQ plus SQ minus, Q can be any integer. So we will go up to 2, +1 and +2, and then SQ plus is decaying to fermion-fermion pair and SQ minus is similarly decaying to fermion-fermion pair. So what we did is the experimental collaboration and phenomenological recurse, so they place exclusion bounds on the production cross section times the branching ratio, and they show their plot in the as a function of mass of this charge scalar till 95% confidence in limit. So this includes the production cross section times the branching ratio. We generated this process and we denote the sigma 95 to be this cross section given by the collaborations, and sigma 95 by sigma production cross section which we generated till NLO QCD at MATGRAPH. We interpreted the model file at fine rules, used the NLO CT package and generated at QCD NLO production cross section, and where this can be reduced to branching ratio should be less than root over of this quantity. So given this numerator and denominator, we can actually find the limit on branching ratio as a function of mass of this charge scalar. So here is our result for same sign dilepton final state. Here from the existent models we have the +1, +half and 0 T3 eigenvalues where the colored lines are shown, and this is the doubly charged mass, and same sign dilepton atlas bound is this shaded area, and this can be translated to the branching ratio mass plane via this formula, and here we can see as from here you see till like 1100 or so the masses are excluded for T3 is equal to 1. So here you can see this is the red line and the branching ratio can go up to like less than 0.4. So here are our theoretical cross sections and comparison with the experimental collaboration. Same can be shown for same sign diboson final state. Here the cross section is same, like This is the same, the mass scale is different, it's from 400 to like 1300, but here you see for the same sign diboson final state, the W plus, W plus, W minus, the 4W final state, the bounds are not really strong till now. So we can exclude this up to 350 GeV, and this 350 GeV bound for T3 is equal to +1 can be translated to the branching ratio till this point. And here also this is the bound is taken from Atlas, and this plot can be translated easily into this branching ratio mass plane. And what is the novel feature here? Given a T3 number that is can be originated from any BSM model depending on their doublet triplet structure, given a mass you can actually directly tell what can be the branching ratio. So there is no, if you use this toolkit, there is no need to recast your analysis for model by model. So this can be done for singly charged scalars also. Here we have many final states. The most promising one is W plus gamma, the other one is W plus Z, and can be the mixed state thing for the charge scalar when one charge scalar is decaying to W gamma and the other is decaying to WZ. So here you see all the T3 values are presented, and here also we include QCD NLO correction through NLOCT package, and these can be constraints for T3 equals to -1 up to like 500 or so. So here are two nice plots, so which shows this left one is for W plus gamma, which shows the same thing till like after 500 we have T3 equals to -1, and for WZ you have this below 300. So again, given the isospin quantum number and given a mass, without going into your model specific numerical analysis, you can refer to this kind of plots and refer what could be the branching ratio for your charge thicks, doubly charge thicks, singly charge thicks, any kind of thicks. So we cross-validated our result for specific example, which can be a type 2 seesaw, and as we know there exists the triplet, and here the specific feature of type 2 seesaw is the branching ratio depends on mass as well as the triplet wave. So it is a 2-parameter function. So here we see that in the mass VT plane, this area is excluded for the WW production channel, and up to 350 GeV is excluded as I showed earlier, and for the dilepton final state it's going till 1000, and much lower VT is excluded because in type 2 seesaw the charge thicks decays to W plus W, either W plus W plus or to L plus L plus depending on this triplet wave. So as I showed in the table, there exists Georgi-Massachev model where there also the doubly charged scalar exists. So depending on the structure of Georgi-Massachev model and type 2 seesaw, there is no difference between this H plus plus, and as long as the Drelian pair production is considered, we will end up with having the same bound. And for Georgi-Massachev model, we also check that the singly charged scalar is coming from a mixture of T3 equals to 0 and T3 is equal to 1 from H3 plus and H5 plus, so to say. So there also we can recast the same bound. So this is the example and cross validation. So the main advertise is the point is that, so you don't have to recast all your BSM models and to use all the numerical facilities available. Just identify the isospin, identify the electric charge, go back to the mass versus branching ratio and identify your mass, isospin, and you will get the branching ratio from this toolkit. So I will conclude that this is a quite streamlined and model independent approach, focusing on the basic properties like mass, electric charge and isospin quantum number. You can actually get these bounds, and this is suitable for a class of BSM model where this kind of charge scalar exists, and as we know from our experience that Atlas and CMS routinely employ this kind of searches and they just present their way, in a model dependent way, and we validated this from these specific examples. And one can expect that vector boson fusion might be important here, but VBA produce a smaller cross section compared to the real one production, and this streamlined analysis can be actually employed in any kind of collider, future colliders and the current colliders, and also the past colliders. So from CDF PP bar collision, there exists the search bounds for doubly charged scalars, and there we also can employ this kind of analysis. And this approach could be a nice bridge between the experimental community and the phenomenologists when they do the recast analysis. So this is what I had to say, and that's it. Thank you. Questions?
Thank you, Samadrita. And questions?
Hello. Yeah. So, have you assumed that these particles are narrow width kind of thing?
Yeah, I assume that they are decaying to this fermion or boson final state to be 100%, and narrow width approximation has been taken.
Otherwise, you can have interference.
Otherwise,
right?
I cannot conclude these results.
And for singly charged particle, sorry, that say H plus minus or something, S plus minus. So single production can be important, right? In that case.
Yeah, single production can be important, but here this analysis holds for the pair production only.
But like, from where the strongest bound comes, or like some
so
particle.
For singly charged particles, actually the strongest bound comes from the single production. When H plus is produced in one pair, but for the Draylian, the generalized aspect, so you should consider the pair production. However, for pair production of charge shift, there exists no such analysis till now. So for H plus H minus kind of pair production, as far as I know, so there is no such bounds. But as you said, the single production of H plus is important, searching the charge states. Yes, yes. Septet is a nasty model. It has many kind of.
I haven't heard of any particle having a plus 3 spin. So
No, there is not till now, whatever we know. But
that's new physics.
There is new physics. There can be new physics, and people construct this kind of model to address many shortcomings in their own motivated way.
Yes, thanks.
Yeah.
Since there is no further question, let's thank the speaker. Thank you for the nice talk.